Hi guys, we're back, and this time we're going to think about how all these forces that we've talked about, like high and low pressure zones, warming and cooling air, rising and sinking, and the Coriolis effect, come together to create patterns of global wind circulation around the planet. So kind of putting it all together, and I'm going to share my screen so that we can look at some images together. Okay, so first of all, I want to kind of speak a little bit about some persistent and dominant locations of high and low pressure zones around the planet and just talk about some of the characteristics. So the first one that I want to mention is right at the equator or around the equator, and it's called the ITCZ zone, which stands for the Intertropical Convergence Zone. So it's right at the center of the tropics, and that we know has a latitude of 0 degrees. And this is a region that's sometimes called the doldrums. And the reason that is because this point right at the center of the two tropical regions is a place where there's a convergence of winds from the northern and southern hemisphere. And we're going to talk more about those in a few minutes. But because the winds from the northern and southern hemisphere meet here and they're at very equal strength, there's actually very little movement of wind across the equator. The two winds from either hemisphere essentially kind of cancel each other out, and there's this kind of stagnant zone with very little wind. And so many hundreds of years ago, people that were trying to sail across the oceans would sometimes come across the equator and they would get stuck. Because there would just be no wind, and they would have to sometimes wait for months until the seasons change and the rotation of the earth changed enough so that they would start to get some kind of winter or summer winds from one hemisphere or the other. And another very consistent thing about the Intertropical Convergence Zone is this convergence of winds from the opposite hemispheres causes winds that are coming together to be pushed upwards like a fountain. We also know that this is a really hot area of the planet. We know hot air rises. So there's this very consistent upward motion of air off the equator. And as we'll talk a little bit about in a couple weeks, this vertical motion of air causes moisture to be squeezed out of the air, and a lot of clouds and thunderheads form. And so you can usually pick out the position of the equator from space because it is consistently lined by clouds, and it's actually the rainiest place on the earth. And as we'll also talk about in a month or so, that's not a mistake that the rainforests exist along the equator. And that has to do with this consistent vertical air motion in this location. So here's two different images of the Earth, and you can see this kind of horizontal line, which represents the ITCZ zone, or the Intertropical Convergence Zone, along the equator. And this is a low pressure zone. Okay, the next zone that I want to talk about is positioned both in the northern hemisphere and in the southern hemisphere at about 30 degrees latitude. And these are areas that are called subtropical high pressure zones. So they're not really in the tropics, they're a little bit below the tropics, a little bit outside the tropics, but they're still pretty warm because they're near the center of the earth. And these are areas that are high pressure zones where air is sinking rather than moving upwards. And we know that when air moves upwards, it sucks other air in towards it. And so low pressure zones tend to be quite stormy areas, whereas high pressure zones tend to be very stable. They don't have a lot of air motion, and they don't tend to create a lot of storms. The lack of air moving upwards and also the lack of air being sucked in from other places causes these to be fairly pleasant. So if you think about going on some sort of quote unquote tropical vacation to somewhere like Hawaii or somewhere like Tahiti or somewhere like Mexico, you're probably not actually going to the true tropics at all. The intertropical convergence zone is extremely stormy. It's not really a pleasant vacation spot, but instead it's these other places that are around 30 degrees latitude that have what many of us think of as kind of like a tropical island feel. These areas are really in the subtropics, and these are very characteristic of the climate patterns that we see in areas around 30 degrees latitude. So again, this would be like Hawaii, many parts of Mexico, even places like San Diego or Florida or the Caribbean. These are places that are gonna be in this subtropical high pressure zone. Okay, as we go farther north or south and we approach 30 degrees latitude, we get into another low pressure zone. And again, low pressure zones are created where air is rising. And now 60-degree latitude is up in places like Alaska and places like Patagonia in the southern hemisphere. So these areas are not warm. So it's not like the air is rising here because it's getting super hot, but these areas are relatively warmer compared to the poles, which are at even higher latitudes. So air that's moving down from the poles in the northern hemisphere or up from the poles in the southern hemisphere is warming as it moves towards the equator. And once it gets to about 60 degrees latitude, it's relatively warmer enough compared to the areas at higher latitudes nearby that it will start to rise up off the surface of the planet. And as with the low pressure zones at the tropics, this rising air causes moisture and other air masses from around to get sucked in towards these low pressure zones. Also, the rising air itself creates clouds. And so these low pressure zones tend to be super stormy as well. And so if you've seen images of Alaska, you know it's kind of a harsh climate. There's a TV show on that my husband used to be very into called The Deadliest Catch, where people go out fishing for like salmon and crab and these really harsh stormy conditions out in the seas outside Alaska. And this is the type of climate that we would expect to see from these subpolar low pressure zones. And then finally, once we get all the way up to the poles, the weather is actually quite stable. So these are also high pressure zones where cool air is sinking. And just like the high pressure zones at the 30-degree latitude, the areas at the poles actually have very stable air. So we think of places like the South Pole and the North Pole as perhaps being very stormy because they're very snowy, but they're just very snowy because it's so cold here throughout the year that the snow really doesn't melt. But they actually get very, very little new precipitation in terms of rain because it's too cold for that, or snow in any given year. And they're actually some of the driest places on the planet, the places that get the very lowest amount of precipitation. So in terms of moisture, these areas are actually deserts. And this is an image of the North Pole, and this is kind of illustrating what we talked about a couple weeks ago, where the sun in the northern hemisphere doesn't set during the summertime because the North Pole is tilted towards the sun. So even at like midnight, 2, 3 in the morning, the sun just gets down to the horizon and then comes back up again during the day, which doesn't necessarily have to do with the fact that it's a high pressure zone, but just thinking about other characteristics of this zone. So to review, we have low pressure zones at the equator, high pressure zones at 30 degrees latitude, low pressure zones at 60 degrees latitude, and high pressure zones at the poles. Okay, so what this creates is this pattern around the planet where we have low pressure zones that are shown in these blue colors. And so we have some low pressure around the equator, and then we have higher pressures shown in yellows and oranges around 30 degrees. So again, places like Hawaii, Mexico, San Diego, Florida, North Africa, etc., also in the southern hemisphere. Then we have low pressure zones again up around 60 degrees latitude, and this is a little bit more dominant and more extreme in the southern hemisphere where there's less land mass, which has a little bit of disruption of these patterns. There's more landmass in the northern hemisphere, less landmass in the southern hemisphere. And then you can't really see from the view of this particular map, but we would also expect to see higher pressure zones up near the poles. So this is the kind of patterns that we see around the planet. Okay, so in response to these high and low pressure zones, and then also it's kind of a chicken and the egg thing, creating these low and high pressure zones are these vertical cells, we call them, or vertical convection cells. So we've talked about convection before, this rising and sinking of a fluid like air because of differences in temperature. And so the air does not flow directly from the poles all the way down to the equator. That's something that we've kind of said might be a real simplistic idea of what happens on the Earth. It's not what we actually see, but instead we have multiple convection cells within each hemisphere. So between 0 and 30 degrees latitude, we have something that are called the Hadley cells. And so hot air rises up off the equator, and then it moves outwards away from the equator like a fountain. In the upper atmosphere, it cools off and eventually gets cool enough as it approaches latitudes of around 30 degrees, both in the southern and northern hemisphere, and it starts to sink back down. And it doesn't stay cold, it heats up as it sinks. So by the time it gets down to the ground, it's warm again. And then it moves from that high pressure zone that's created by the sinking air around 30 degrees latitude back towards the poles. So that is called the Hadley cell, this vertical convection cell between 0 and 30 degrees latitude. Then there's a what's called a Ferrel cell, or sometimes a mid-latitude cell, where the sinking air that's coming down around 30 degrees latitude is pushed outwards, not only back down towards the equator, but also upwards towards the poles. And it moves northwards in that position, and that creates a convection cell there. That's called the Ferrel cell, or the mid-latitude cell. And then finally, there's another cell that's called the polar cell, where air sinks down at the North Pole is easier to see in this particular image. And then the air pushes outwards, out from the polar area, down towards, lower latitudes. And as I already mentioned, it kind of warms up as it moves southward. It's not as warm as it would be at the equator, but warmer than the poles. So by the time it gets to around 60 degrees latitude, the air is rising off the surface at that location, which feeds in both to the Ferrel cell that we just mentioned, and then also into the polar cell. So the air that rises up around 60 degrees latitude, some of it's pushed southwards as part of the Ferrel cell, and some of it's pushed northwards as part of the polar cell. And we have a mirror image, but the same concept that's happening in the southern hemisphere as well. So we basically have these 6 convection cells on the planet, 3 in each hemisphere. First the Hadley cells, and then moving out from the equator, the Ferrel cells, and then moving out even farther, the polar cells. So this vertical air motion is going to be contributing to the fact that we have low pressures that we just mentioned at the ITCZ zone at 0 degrees latitude, high pressures that we call the subtropical high pressure zones around 30 degrees latitude, where the Hadley cell air is sinking. And then we have subpolar low pressure zones at 60 degrees north and south latitude, where polar air is rising. And then we have the polar high pressure zones, where the coldest air is sinking up at the North Pole and the South Pole. So just like we talked about conceptually earlier in a couple lectures ago, the vertical motion of the air driven by temperature differences is influencing the pressure conditions at the surface. Okay, so what we end up seeing is that we have the intertropical convergence zone, the low pressure zone, the subtropical high pressure zone at 60 degrees, the subpolar low pressure zones, and then the high pressure zones. And then we have surface winds moving towards the low pressure zones and away from the high pressure zones. So we have winds that are moving towards the equator, because the equator is a low pressure zone. These winds are called the trade winds. So we see winds moving towards the equator. They're not moving in straight lines because of the Coriolis effect. And the northern hemisphere, they're bending to the right from their direction of motion. In the southern hemisphere, they're bending to the left. Or remember, the other rule we learned in the Coriolis effect is if they're moving towards the equator, they're going to be bending and pointing towards the west, which is what they're doing in this image. Between 30 and 60 degrees, which is kind of the base of the Ferrel cell, the air is moving away from a subtropical high pressure zone. In the northern hemisphere, it's arcing to the right, and the southern hemisphere, it's arcing to the left. Or these winds are both moving away from the equator, so they're going to be moving from an area where they have a faster rotational velocity towards an area with a slower rotational velocity. They're going to overshoot their target, and they're going to be pointing to the east. Okay, and then somewhat confusingly, those winds are called westerly winds because winds are named from the direction from which they come, not the direction where they're going to. So they're pointing to the east, but they're coming from the west. So these mid-latitude winds are called westerly winds, while the southern, winds near the equator are called often trade winds, but trade winds are an example of easterly winds. And then finally, in the polar regions, we have winds that are being moved out from the 90-degree latitudes areas near the poles, being sucked towards the low pressure zones around 60 degrees latitude, these subpolar low pressure zones. In the northern hemisphere, they're moving to the right from the direction of motion. In the southern hemisphere, they're moving to the left. They're moving towards the equator. So they're moving from an area of lower rotational velocity to higher rotational velocity. So the Earth is spinning out from underneath them. From where they're going, it appears that they're bending to the west, because that's another rule that we know from the Coriolis effect. So they're bending towards the west, which means they're coming from the east. So these are easterly winds. And these winds that we see are very dominant, very consistent global circulation patterns that really dominate the impacts that we see to climate and then also to biology around the planet. And so this is something that I expect you guys to learn, that I'll test you on. And so I want to walk through it one more time, a little bit more slowly on the next slide. Okay, so here's an image of the Earth. Okay, with the equator, 0 degrees latitude, 30 degrees latitude, 60 degrees latitude, up at the poles. We know that the equator is the hottest area and the poles are the coldest area. So we know that the equator has consistent low pressure and the poles have consistent high pressure. So hopefully that's the kind of thing that you could recreate on your own. By the way, I have some images like this one that I'm working through right now on the Canvas site for you guys to practice with to help you understand. Okay, so if we want to kind of build out this pattern of global circulation, it's important for us to understand how it works. Trying to memorize it is not a good approach. You want to understand the concepts so that you can rebuild it every time, and knowing that the equator is hot and creates low pressure from rising air, and that the poles are cold and create high pressure from sinking air is a great place to start. If you know that piece of information, you should be able to rebuild this picture of global circulation. So the next thing that I'll put in is that we have rising air and sinking air off the hot places and cold places. Okay. Also, we mentioned, to declutter this diagram, I'm not going to include all of the Hadley cells, Ferrel cells, and polar cells, but we know that the air that rises up off the equator sinks back down around 30 degrees, and the air that sinks down to the poles moves across the surface and rises back up around 60 degrees. So we don't just have one area of rising air and then two areas at the poles of sinking air, but we have these alternating zones in the northern and southern hemisphere of rising and sinking air about every 30 degrees. So you can remember that it always flip-flops. We have low pressure here, and then high pressure where air is sinking, low pressure where air is rising, high pressure where air is sinking. You can see that it's always switching off. We don't ever have two areas of low pressure next to each other or two areas of high pressure next to each other. And then also the northern and southern hemispheres are complete mirror images of each other. So you can kind of test yourself by making sure that you have your northern and southern hemisphere as mirror images. Okay, now that we know where the low and high pressure zones are located, I started out on this diagram with these little kind of light arrows, and these arrows don't necessarily show wind direction, but what they do show is that they're pointing towards low pressure zones and they're pointing away from high pressure zones. So one of the fundamental things that we learned about winds this week is they always move down gradient from higher pressure to low pressure. So we'll generally expect winds to be moving towards these low pressure zones, and we'll generally expect winds to be moving away from these high pressure zones. Okay, but we also know that they don't move in straight lines. The Coriolis effect and these differences in rotational velocity of different parts of the Earth cause the winds to be deflected as they move from one latitude to another. Okay, so what we see, first of all, is the trade winds. The trade winds are these easterly winds that converge towards the equator. And we can see that they're moving from both the northern hemisphere and the southern hemisphere towards the equator, towards the low pressure zone, but they're not going straight towards the low pressure zone. They're being deflected, and they're being deflected towards the west because they're moving towards a location with faster velocity, and the Earth is kind of speeding out from underneath of them. So they're ending up behind their intended target. We could also note that they're being deflected to the right in the northern hemisphere and to the left in the southern hemisphere. And remember, that's to the right from the direction of motion. So if you imagine you're like a runner or you're in a car or on a bike, moving from this position, you would have to move to your right to follow this path, even though this arrow is pointing to our left as we're looking at it. Okay, so these winds are very consistent winds that we said are very important to influence global climate. They flow between 30 degrees latitude and towards the equator very consistently. They're called the trade winds. They're called the trade winds because historically people would sail from places in Europe, and they would sail down along Spain, along West Africa, and then they would hop on the trade winds to come over to the Americas to trade and rape and pillage, etc. So anyway, that's why they're called the trade winds. Okay, the next set of winds are called westerly winds, and these are the winds that blow kind of at the base of the Ferrel cells, and they are moving away from the high pressure zones at 30 degrees latitude. So then we know that the winds are moving away from that area towards higher latitudes, but they're not moving in a straight line. They're being deflected to the right in the northern hemisphere, to the left in the southern hemisphere, or we could think of the fact, since they're moving away from the equator, they're moving from an area of faster rotational velocity to an area of slower rotational velocity. They're going to end up moving faster than the other objects and materials in the place where they end up. They're going to overshoot their target and end up to the east. So we have these winds that are called westerly winds because they move from the west to the east, and they're mirror images across the equator. And then finally, we have what are called polar easterlies, the winds that move from the high pressure at the poles towards the low pressure at 60 degrees latitude. They don't move in a straight line. They bend to the right in the northern hemisphere, to the left in the southern hemisphere, or because they're moving from an area of slower rotational velocity to faster rotational velocity, the Earth is rotating out from under them and they're ending up behind their target to the west. So they're moving from the east to the west, called polar easterlies. So again, I have these images on Canvas for you to practice with. This is the kind of thing I would ask questions about on the midterm. I do expect that you would be able to recreate this kind of thing. And so please do spend some time trying to work through it and make sure that you understand. Okay, here's one more image, the whole shebang, all the different parts together. So we have this vertical air motion, the Hadley, Ferrel, and polar cells created by zones of relatively warmer and relatively colder surface temperatures. And then that causes surface winds. Basically, the bottoms of each of these cells are the trade winds, the westerly winds, and the polar easterlies. And then the orange arrows are representing the surface winds, the bottoms of each of these cells. So the orange winds here represent the trade winds. The orange winds in the middle latitudes represent the westerly winds. And then the orange winds, which are a little bit hard to see in this diagram, in the polar regions represent the polar easterlies. Okay, so then the last thing I want to show you guys here is what this kind of typically looks like in the parts of the Western United States where we live. So we have a consistent high pressure zone here down near northern Mexico and San Diego. And remember, high pressure zones don't really suck in air, they have very stable air. Then we have low pressure zones up here near Canada, which are pulling in air. So air is coming from the west towards the east, coming this direction. The westerly winds, they're being pulled in by the low pressure zones. When there's extreme low pressure zones, that will suck air in and it will pull to the right in the northern hemisphere to create these counterclockwise storms. And then below the low pressure zone, we have winds that are moving the opposite way from the east towards the west. These are the trade winds that blow through places in Mexico and Central America, and then down towards the equator. So this is a very kind of consistent weather pattern that we would see in our part of the world, where central and southern Mexico is a lot wetter and rainier. Northern Mexico and Southern California and places like Arizona are very, very consistently dry. And then Northern California a little bit, and then Oregon and Washington are much wetter as air is moving off the ocean and being pulled into that location. So that's the kind of typical climate that we see because of our position within the global atmospheric circulation pattern. Okay, that's a good stopping point.